Okay, we'll start. Good evening, and sorry for the delay. I just came back home and managed to start somehow. Right. Am I audible? Right, let me also check. Am I audible? And yeah, audible, right? Right. Am I audible? Okay. Right. Let's start. My video is also fine now. Okay. Right, we'll start. Yes, okay. Right, we'll start. If you haven't downloaded the questions yet, right, I have pinned a message here in the live chat. So you can go there and download the questions. If you haven't downloaded the question, right, I have pinned a message here in the live chat, right? Just go there and make sure you have downloaded the questions. Sorry, I couldn't put the questions a little bit early today because I was onto something and was out of the class and now only came back. Right. Okay, we'll go to the discussion. Right. I hope you have got the questions now. Right. I hope you have got the questions. Right. Let me share the screen first. Right. Is it visible? Visible, right? Okay. Okay. Visible now? Right. All right, then we'll go to the discussion. Right. And before starting, now we are on the day 17 of S2A, right? We are in the day 17 of S2A, and you are 6 weeks from the exam, right? Just 6 weeks. 6 weeks. So manage your time. Whatever you do these days is going to be returning you as an investment, right? So always you will get a return on the investment you do these days, right? Always you will get a return on the investment you do these days, right? So be very careful and conscious about time these days and manage it effectively among all three subjects, right? This is not about managing only one subject, right? This is all about managing all three subjects, right? So therefore, managing time is very much important these days, right? Very much important these days. That is the most important thing actually. So while you are covering up the things like you have to go through theory parts, structured essays, papers, paper classes, write papers, right? Practice papers, and after the discussions happen, then evaluations, self-evaluations, right? Many things, and in all three subjects, not just here in physics, no, in all three subjects, right? So managing time is the thing here, and you will have 2 or 3 more exams from the school, right? Final term or the pilot exams, right? So likewise, in some schools there will be 2 term tests or 2 exams, 2 end exams, and in some schools there are schools they have 3 exams, right? So likewise, from that side also you will be kind of occupied, right? Because of the exams and the class stuff, seminars, right? Because of those things, right? So manage the time. Managing time is the most important thing these days, right? Okay, then let's go to the first one. You are required to determine the refractive index of material of glass prism using a laboratory spectrometer. A. Draw the path of monochromatic ray incident on surface AC undergoing minimum deviation through the prism shown in figure 1. Right. Also mark the angle of incidence I and the angle of refraction R at the surface AC. Right. Listen, now if that says minimum deviation, right? We know at minimum deviation, our ray diagram is symmetric. Our ray diagram should be symmetric across the prism angle, right? Should be symmetric across the prism angle, right? Then that is very important when you draw the diagram. Otherwise, if that diagram is asymmetric, no marks will be given, right? It should be a symmetric one. When there is symmetric, always the refracted ray becomes parallel to bottom, BC. Always refracted ray becomes parallel to bottom, right? Second, right, right. See, let me use the ruler. Say this one is the incident ray. Say this one is the incident ray, right? And here this one is the refracted ray. Neglect the unwanted parts, right? Now it's correct. And say this is the emergent ray, right? Right, now fine now. Then have to draw the normals. Then here we have one normal, and here we have another normal for this surface, right? Then angle of incidence is here, right? Have to put these arrows also. Putting arrows is a must, right? Putting arrows is a must, right? And angle of refraction is here, or angle of refraction. Then angle of deviation is the angle between the original direction of light ray, this one, and the final direction of light ray, this one. Angle of deviation is here, right? So this is how it should be, right? Next, mark the angle of minimum deviation D. I marked it already. Mark the angle of minimum deviation D on the of the ray in the above figure 1. Write down an expression for the refractive index N of material of prism in terms of angle of prism A and D. Right, that's a proved equation. Right? We know N equals, right? It's a proved equation. No? That's a proved equation. N equals, we know, sine A plus D over 2 over sine A over 2. That's a proved equation, right? Next one, give the experimental steps needed for adjusting the telescope of spectrometer, right? So when we adjust the telescope, there are steps, there are sequence in those steps, right? First thing is, in telescope, we know it consists of eyepiece and objective piece. First of all, we have to adjust the eyepiece, right? To adjust eyepiece, what we do is, right, first listen, to adjust eyepiece, what we do is, have to adjust the eyepiece until a clear sharp image or a clear symmetric image of crosswires are seen, right? Then once the eyepiece is adjusted, then telescope should be rotated and focused to a distant linear object, and the image of a clear symmetric image of that distant linear object can be a tree or can be a pole, a column, something like that. Distant linear object, and a clear symmetric image should be taken to the crosswires again. Then from the first step, eyepiece will be adjusted. From the second step, objective piece is adjusted. When both are adjusted only, right, telescope will be adjusted. Okay, right, this way. First one, adjust the eyepiece. Adjust the eyepiece until a clear symmetric image of crosswires is seen, right? That is the adjustment of eyepiece, and then the adjustment of objective piece. For that, you have to focus it to a distant object, right? Then focus telescope to a distant object, distant linear object, to a distant linear object, and adjust objective piece. Right? No need to adjust the eyepiece again because that is already adjusted from the first step. Right? Now second one, focus telescope to a distant linear object and adjust objective piece until a clear symmetric image of object is seen on crosswires. Right? These two are the two complete answers. Right? The given space is enough. Right? Now when I write here on the screen, this is not my usual handwriting. I mean the size. This is not my usual size of handwriting. Right? I'm writing a little bit larger to you to see properly. Otherwise, the given space is enough. You have to manage the space to write this thing within 3 lines. Right? Next, a student argues that a beam of light from a bright filament bulb can be used for the leveling prism table. Do you agree? Beam of light from a filament bulb. Yes, possible. What's the reason? When we level the prism table, right, what we use is the reflection of light. No? To level the prism table, we use the reflection of light, not the refraction. That's the reflection. Since there is reflection, right? Whether we use a monochromatic light or white light or any other bulb, doesn't matter. That's a reflection always. Doesn't matter. Right? Then the question is, do you agree? Yes, we agree. Give the reason. Reason is to level the prism table, right? We use the reflection of light, right? Then no issue. Give the reason. Reflection of light is used. Reflection of light. Reflection of light is used to level the prism table. Right? Now, if it was a case regarding refraction, then it matters because due to refraction, color dispersion occurs, no? Right? If white light use if the color disperses. But here, since there is a reflection, no worries, totally fine. Right? F. After adjusting all the parts of the spectrometer, how do you experimentally obtain the minimum deviation position for the monochromatic ray of light? Right. Monochromatic ray of light. Okay. Monochromatic ray of light. Right. For that, it should be monochromatic because for minimum deviation, we use refraction. Refraction white light use that's a refraction. That's the thing. Right. Then how to mention these steps in the correct sequence. These steps should be mentioned in the correct sequence. Right. Right this way. Usually we use a sodium lamp. Right. Usually we use a sodium lamp in the lab. That is called the sodium lamp. In the experiment also, when we do the discussion, practical seminar, also I told you that is called a sodium lamp. Right. That is called a sodium lamp. Then since that word is given in the guide always, you have to use that word sodium lamp. Right. Then have to say that use or keep a sodium lamp in front of keep a sodium lamp keep a sodium lamp in front of objective piece of telescope, or in front of objective piece, right? Objective piece. And when keeping the prism, there are things to be followed. Now, no need to mention everything here, right? Then when we keep the prism, we know something additional, but this is background related, right? When you keep the prism, one vertex of the prism should be at the center of the prism table, and one side of the prism should be perpendicular to a line connects two pins on the prism table. PQR pins, right? Over there the end, right? Then next one, keep the prism on prism table properly. Properly means that should be how I explain, right? Properly. And we are going to get the small angles, no, right? We are going to get the small angles, right? After keeping this, have to rotate it to a small angle, right? Have to rotate it to a small angle of incidence, right? Keep the prism on prism table properly, and rotate, adjust or rotate, adjust scale and adjust the table to get a small angle of incidence, a small angle of incidence, right? Now, here comes the most important thing, right? Here comes the most important thing. Now, we have to rotate the prism table, right? We have to rotate the prism table by looking through the opposite side of the prism, right? I have to rotate the prism table by looking through the opposite side of the prism, and we will see one position, right? We will see one position, right? At that point, the image returns, right? It moves in a particular direction and it turns to the opposite direction, right? That turning point is called the minimum deviation, right? That turning point is called the minimum deviation, right? So turning image is a keyword. Turning image is a keyword. Or switching the direction is a keyword, right? Switching direction, turning, returning, likewise, that is a keyword. That's a keyword. Next one, rotate prism table. Rotate prism table by observing image through opposite surface, right? Surface, and get the reading when the moving direction of image of slit, right? What we see is the image of slit, image of slit. Reading when the moving direction of image of slit is switched, right? That's a complete answer. This idea must be there. Right? G. When the telescope is fixed to a minimum deviation position, the circular scale and the vernier scale positions are shown in the figure 2. What is the reading of the position? Right, what is the reading of the position? Then before vernier 0, see, now we know main scale of spectrometer is in 0.5 degrees, right? Main scale of spectrometer is in 0.5 degrees, right? Main scale. And vernier scale is in minutes. Vernier scale is in minutes, right? Then 140, 141, 42, 43, 44 completed. 144 completed, right? So we know final reading is the reading of main scale plus reading of vernier scale. Then reading of main scale is 144. That is in degrees. 144, right? Then find the coincided point. Coincided point is here, this one, right? 15. Then 15 minutes from the vernier scale, that is directly 15 minutes. 144, 15 minutes. Right? Next. After removing the prism from the prism table, the direct reading of the telescope is measured as 104.55 direct reading. Right? So what is done here is this, no? Quickly now, if this is the prism, right? One reading is taken at the minimum deviation here, say R1, and then the other reading is taken after removing the prism here. Then difference between these two measures the angle. Difference between these two measures the angle, right? Angle of deviation. That's the angle of deviation. Then just the difference between these two is the minimum deviation. That's it. Try right? See. Then that's why direct reading is given. Direct reading is 140, 104, 55. Find the value of D. The 360 mark of the circular scale has not crossed when taking measurements. What's the importance about that? If the 360 mark is crossed, when we take the readings, you have to take reading as 360 minus difference. Right? Now, if that is not crossed, which means both readings are at the same side, get the subtraction. Then D equals, right, from 144, 15, subtract 104, 55, right? Just a simplification, right? 15, 55 again, you have to take 60 from degrees, then 75 minus 55, it becomes 20. Then 143 and 104 means 39. 39, 20, right? 39, 20. I, if the prism angle is 60, calculate the refractive index N of material of prism. Use the natural sign table for your calculation, right? Then have to find some sign value also, right? Then apply now equation. We wrote the equation initially first, right? N equals, right? No need to write again when you are doing this step here. This is for your reference. Sin A plus D over 2 over sin A over 2. Applying the equation. Sin, then A is 60 plus D. D was 39, 20 over 2 over sin A over 2, 60 over 2. Right? 60 plus 39 is 99, 20, no? 99, 20. Then divided by 2, 49, 49, 40, right? 49, 40. Sin 49, 40 over sin 30. Right? Sin 30, we know. Then have to find sin 49, 40. Have to find sin 49, 40. Right? Let me share the value. Sin 49, 40. You can check from the sign table. Right? You can check it from the sign table. It's coming as 0.7622. You also can check with the sign table and see 0.7622. Right? This is half, no? Then that times 2. Right? It is 1.52. It is 1.52. Final answer 1.52. Final answer 1.52. Right? You also can check with the table. Check with the sign table. Right? Right. So we have come to the end of the first question. Right? Ask if anything before moving on to the second. Right, ask if anything before moving on to the second. Give me 1 minute. One second. Since new batch 420 is starting tomorrow, right? Inquiries are coming, right? So if there's anyone willing to join for 28 batch, right? Second batch actually. First batch is already going on, right? If there's anyone who need to join the second batch for 28, if you have any friends, colleagues, relatives, or anyone, you can share the message, right? We are starting the second batch from scratch tomorrow at 7. Okay. Right. Let's go to question 2. Can I explain H part again? H is a subtraction because angle of first diagram angle of deviation is here. No? Angle of deviation is here. Then one reading is taken at this position T1, right? And once the prism is removed, right, the straight reading is taken here T2. Then angle between the value between T1 and T2 is the angle between these two lines. That is the angle of minimum deviation. Right, the exact theory we had. Right, that's the exact theory we had. Right, that's why these two are subtracted. Right. Right. Okay, right. Right. Shall we go to second one? Second one. You are asked to, right? You are asked to determine the refractive index N1 of a transparent NL of a transparent liquid using apparent displacement of the image of an object. You are provided with a tall cylinder, sufficient amount of liquid, and a traveling microscope, a small pin, or fine plastic pieces which can float on the liquid, and a large syringe. Fine plastic pieces are given. That's kind of important because other things are the usual general things we have in our general experiment, right? Instead of them, plastic pieces are given which can float on the liquid, and a large syringe. Right. Write down an expression for the apparent displacement D produced by a transparent block made of a material of refractive index N and thickness H placed in air when an object O is placed at the opposite side of a block as shown in the figure. Okay. Then we know our root D equation for apparent displacement is this, no? D equals T, simple T, D equals simple T thickness 1 minus N2 over N1. This is our proved equation. 1 minus N2 over N1. N2 is observer's medium. N2 observer's medium. Right? N1 object's medium. Then apply these terms here. Then apparent displacement is D. Right? Thickness of the medium is given as H. 1 minus I is kept at air. This is at air. Then 1 over N. Right? That should be it. Right? That's a proved equation. Apply these terms accordingly. Apply the terms accordingly. B. As in figure 2, the small pin O is placed at the bottom of the empty cylinder. The traveling microscope is focused from above to view a clear image of O and reading is taken. Say X. Right. The initial reading. Reading X. This reading is taken. Next. Then the liquid is poured up to a certain height, H. Right. Then a liquid is poured up to a certain height. Right. We know when the liquid is poured, there will be an image of this somewhere here. That's the displaced image. Right. There will be an image of this somewhere above the object. So this is I. Right. Certain height H. Okay. Then this height is given H. Okay, then first one, what should you do to the traveling microscope to see a clear image of pin again? Let microscope reading be Y in the case, right? Then this is Y. In that case, then what we have to do is you have to move the microscope upwards, right? Move the traveling microscope upwards until a clear image of pin is seen again, right? Because when you see this image, Y, this one, when you see the image at Y, right? Again, it should be a clear image to the telescope, right? For that, now initially it was focused to point O, no? Now it should be focused to I. To focus to I should be taken upwards to adjust the gap, right? Then write down, move traveling microscope upwards, right? Move traveling microscope upwards until a clear image of pin is seen. Until a clear image of pin is seen, right? Then part 2, write down the experimental steps that you follow to measure the height H of the liquid column. Let the reading be Z, right? For that, what are we using usually? In the practical seminar about the experiment, I mentioned a specific name for this powder that is called lycopodium powder, right? Right? We discussed it. That was called lycopodium powder. Now here in this case, instead of lycopodium powder, right? That's why this is important. Plastic pieces are given. Now without using lycopodium powder, right? We can float plastic pieces, right? Fine means small plastic pieces on the liquid because it says it floats on the liquid to take that reading. Otherwise, usually in the standard experiment, what we do is lycopodium powder. What we use is lycopodium powder, right? Now here, without using lycopodium powder, we have to use plastic cubes because plastic pieces, because that is what is given here. That is what is specifically given here, right? Right. Write down the experimental steps that you would follow to measure Z. Now Z is here. May reading a gun only. C is here, right? Then right, float few fine plastic pieces on the liquid, and move microscope upwards until it is focused to plastic pieces. until it is focused to plastic pieces. Until it is focused to plastic pieces, right? Now the readings are like, when it is focused to plastic pieces, which means, right, it is focused to a point at the level of the liquid, at the surface of the liquid, right? At the surface of the liquid. Then if that reading is taken, we have this reading Z to get here. Z, Y, and X. These three are the three readings we have now. These three are the three readings we have got now. Right. Now, write down expressions for height h of liquid column and the apparent displacement d of the image using the readings x, y, z. Right. We know apparent displacement is the difference between real depth and apparent depth. Then apparent displacement is from here to here. See, let me use a different color. Apparent displacement is from here to here, d. This is the apparent displacement. Right, Marian? This is the apparent displacement, d. Right, now, when they are marked in a diagram like this, easily we can see what's happening. Then h is given by z minus x. And apparent displacement is given by y minus x. Very simple. Z minus x and y minus x. Right? So likewise, mark it on a diagram, then it makes more sense. It makes more sense. Right? Now usually we don't draw a graph here when we do the standard experiment, but in this particular question, right, now we are guided through a graph. Right, now we have to adjust ourselves and go ahead with the question. Right, if this expression you have written in part A above is used to determine the refractive index of the liquid NL using a graphical method. Graphical method, what is the variable that you are going to change in it? Right, from that equation, from this N is a constant, because for a liquid refractive index is a constant, we can't change it, right? Then variables are h and d. From that also possibly we can change, or practically we can change is h, right? Because we can't change apparent displacement automatically changes if h is changed. Then our independent variable must be h. Right, then what is the variable that you are going to change in it? H. Right, because only variable that we can use is h. What will be the dependent variable? Dependent is d, apparent displacement. Right, without mentioning as h and d, if you mention it as height of liquid and apparent displacement also, that's fine. Right, without mentioning in letters, that's also fine. Fill label in the axis, sketch the graph. Right, then it goes d equals h times 1 minus 1 over n. Identify these variables, then 1 minus 1 over n h. See, now this is our x-axis. This is our x-axis, right? This is the x-axis, right? Should be in centimeters or meters. Then this is our y-axis. Should be in centimeters or meters. This is our y-axis. Then whatever it is as a product with x is gradient. Then graph is y equals mx. Graph is mx. Right? Graphing. D. Obtain an expression for the refractive index in L in terms of the gradient of the graph. Right. Now we know what gradient is. See, gradient is 1 minus 1 over n. Right? 1 over n, n is nl now. Yeah, n is nl now. NL. Right? NL. Then we know gradient is 1 minus 1 over nl. Obtain an expression for nl now. Then subject nl from this. Subject nl. Switch terms. Then 1 over nl. Right? If you switch terms, 1 over nl equals 1 minus m. No? 1 minus m. Then we need nl. Right? Upside down. Put upside down. Then 1 over 1 minus m. 1 over 1 minus m. Right? We have to be with the flow, right? So nicely, it's going with the flow. If the gradient m equals 0.2, calculate the value of refractive index NL of the liquid. Right, then NL is, right, just apply here 1 over 1 minus 0.2. Then 1 over 0.8. 1 over 0.8 is 1.25. No? 1.25. Right? Then next F, a small calculation again. When the height of the liquid column is 5 centimeters, water is slowly poured so that the liquid floats on water. Right now, two liquids are here. Right now, two liquids are here. Then, so that the liquid floats on water. Right, something like this. Now here we have water and liquid. Right, we have water and liquid in this case too. Now, right, liquid column 5 centimeters. Then this height is 5 centimeters. Right. So that the liquid floats on water. The total apparent displacement of the image of the pin is 1.5 centimeters. Total is given. And the refractive index of water is 4/3. Right. This is given 4/3. Refractive index of liquid was found, no? Right. Refractive index of liquid was found. That was 1.25. This is also known. 1.25. That is known. Calculate the height of water column in the cylinder. Right. So let's assume this height as HW, H water, right? HW. We know in apparent displacement, total apparent displacement is equal to the addition of or the sum of apparent displacements by each liquid. Then D total equals D of liquid plus D of water, right? Then if we apply this separately, we can find DL and DW separately. To find DL, right? To find DL, apply this to liquid. DL equals height of liquid is known, 5. 1 minus 1 over n 1.25. Right? Then DL equals 5. 1 over 1.25 means 1.25 කියලා කියන්නේ it was 504 ne? It was 504. Then 1 minus 1.25. 1.25 is 504. Then this is 1 minus 405. No? Right. Then DL equals 5 times complementary is 5. 5 minus 4, 1. These two cancels. It comes to 1 centimeter. Then DL is 1. If DL is 1, D total is given as 1.5. DL is 1. DW. Right. Then apparent displacement of water is 0.5 centimeters. If apparent displacement of water is known, then apply this to water again. Right. Same thing. Then DW 0.5 equals height of water 1 minus 1 over 4/3, that is 3/4. 1 minus 4, 1 minus 1 over 4/3, 3/4. Then 0.5 means half, right? 0.5 is half HW. Then 4 minus 3 is 1. This is 1/4. 1/4. 2 times 2 cross multiply, H equals 2 centimeters. That's one. H equals 2 centimeters. 2 centimeters. H equals 2 centimeters. Then H of water, height of water should be 2 centimeters. Height of water must be 2 centimeters. Right? So we have come to the end of that also. Any questions? I need how you got 20. How you got 20? You are referring to the previous one. Previous one. Because 1 degree is 60 minutes. Then 144, right? They are minute simplifications. Then this is 143 degrees. 60 කියලා කියන්නේ 75 minutes. 75 minus 55 from this. Right? මේ දෙක subtract කරා නම් හරි. Right? මේ දෙක subtract කරා නම් 1 degree is 60 minutes. Any questions on this? Is it clear enough? Right, ask if anything and give me 1 second. All right. Is it clear enough? No questions? Seems clear, right? Then shall we go to the third one? You are asked to determine the mass per unit length of a given wire by taking only one measurement. Mass per unit length by taking only one measurement using a sonometer and a tuning fork. Figure shows a standard sonometer setup in school laboratory fixed with the given wire. The wire is stretched with a tension T between two bridges A and B. In this setup, the bridge A is fixed and bridge B is allowed to move. Bridge B is allowed to move. That is important. We can't move both of them then. Then only B is movable. This is fixed. Right? And only B is movable. This is movable. Right? The tension, only B is movable, right? The tension of the wire could be changed by varying the load mass, right? This one. By varying this, additional masses are also given, right? Tension of the wire could be changed, right? So we know if this is mg, tension of the wire comes as T, like this throughout, it will be T, right? A tuning fork with known frequencies provided to you, right? First one, what type of vibrations is produced in the surrounding air due to vibration of tuning fork in the experiment? What type of vibrations? They are longitudinal stationary waves, right? Longitudinal waves or longitudinal stationary waves. Longitudinal air mediums, no? Stationary vibrations or waves. Longitudinal stationary vibrations. If m is the mass per unit length of the stretch wire of tension T, write down an expression for the speed v of transverse waves using T and M, right? Our standard equation, right? V equals root T over M. Our standard equation, the most popular equation. See, in the experiment, you are supposed to measure the resonant length L of wire resonating with the tuning fork at the fundamental note. The student suggested that there can be three ways ABC, keeping the vibrated tuning fork to obtain the resonant state, as shown in figure. XY represents a part of surface of sonometer box, right? XY is the surface of sonometer box. B, tuning fork held normal to XY and without touching, in B, okay. Now only I got it. Tuning fork held normal to XY without touching, right? Make it in without touching. At B, means pen on without touching here, right? And C, tuning fork is held above the stretch wire. Okay. All right, wire is here. In order to obtain maximum amplitude for resonance out of the above three ways, which way would you select to keep the vibrated tuning fork? A, B, or C? Give reasons for your selection. Right? Popular question. That must be A. Must be A. When the tuning fork is kept on the box, on sonometer box only, it transmits energy. Right? It transmits energy to the sonometer box. Right? Otherwise, that propagation of energy or transmission of energy is not that rich. That is not rich. Right? We have to have a very effective or productive, efficient propagation of energy. Right? To increase that propagation, always it should be kept on the box. Right? Then write down. Answer is A. Selection is A. Right? Selection is A. Then have to write the reason, no? Tuning fork should be kept on the box for better propagation of energy, to vibrate air medium inside sonometer with maximum amplitude, right? This is the complete answer. Should be kept on the box. Right? D. Write down the other item that you normally use in this experiment to detect the resonance state experimentally. Right? Other item. Right? We have paper idlers. Right? Now always keep the experiment in mind. Paper idlers. Right? Paper idlers are essential. Otherwise, how to observe or how to identify the maximum amplitude? Right? So what happens is, at the maximum amplitude, when vibrates, paper idlers are jumping off the wire. When they jumps off, then we identify that as the maximum vibration, maximum amplitude, right? Resonance. Then write down the main experimental steps that you would follow to detect the optimum resonance state. Right, optimum resonance state. Right, then have to write what I mentioned. Then write down. First, now paper idlers are not kept yet. No, we have to say that first, right? Have to keep paper idlers. Keep paper idlers on wire AB. Right? Keep paper idlers on wire AB. Right? On wire means around the middle. Around the middle. On wire AB. On wire capital AB. Right? On wire AB. On wire AB. Right? Now, initially it was clearly given that only one is movable. Which one? Only B is movable. No? Then we have to move. Right? We have to move B gradually, right? You have to adjust or move B gradually until paper idlers are jumping off, right? Then next one. Adjust or increase, adjust B gradually. Adjust B gradually, starting from a small length or a small gap between bridges. From a small gap, adjust B gradually, starting from a small gap until paper idlers jump off. Until paper idlers jump off the wire. Right? Next, obtain an expression for M in terms of F, L, and T. Right? Obtain an expression for M. Now we know we have got the fundamental frequency. No? We have got the fundamental frequency. Then this is our fundamental wave pattern on the wire. This is fundamental wave pattern. Right? One loop. No? So we know one loop is lambda 2. Then lambda 2 equals L. In this case, lambda equals 2L. Right? First of all, you have to find it. Lambda equals 2L. Then apply V equals F lambda. V is root TOM. Right? F is F. Lambda is 2L. Right? We need obtain an expression for simple lem. Have to subject simple lem there. Then to subject simple lem, remove the square here. Right? See? Remove the square here. Then TOM equals, this side becomes square of 2 is 4, S squared, L squared. Subject M, then M equals T over 4 F squared, L squared. T over 4 L squared, F squared, L squared. Right? G. If the resonant length that you have obtained in the experiment is small, how do you adjust the above sonometer setup in a suitable manner to obtain a reasonably large resonant length for given tuning fork? Right. Now again, go to this equation, then you can easily argue. It says root TOM equals F times 2L. No? See what we can do to increase L. To increase L, easiest thing to do is increasing T. To increase L, easiest thing to do is increasing T. Fine. That's why these additional weights are also given. With a ribbon, additional weights are given, and in the description also it says that the tension of wire could be changed. Tension of wire could be changed. Right? So that's the purpose. That's the purpose. Then what's the question? How do you adjust? How do you adjust? By adding more masses, right? By adding more masses to the how was it given? To the load mass. By varying the load mass, then by adding more masses to the load mass. Then answer is by adding more masses to the load mass. By adding more masses to the load mass. Load mass. Then tension changes. But if you write as by changing tension, no marks will be given because you can't change tension, right? Tension is something indirect or something happens after changing this. So what we do is changing the mass. No? Right? In structure, it is always, that's how you should write, right? What you do, what we do is adding masses. Due to adding masses, tension changes. That's true. But we can't write as changing tension, right? They are very critical when it comes to structural disease. When M equals 3.2 and F equals 320, the resonant length was found to be 25. Find the mass per unit length of the wire in kgm minus 1. Right? We have the equation now. No? Plug in the equation M equals, right? For the equation here, maybe M equals T. If this is 3.2, right? T is 32. No? 32 over 4 F squared 320 squared, then L squared, L was 25, then 25 times 25 centimeters to meters 10 to the power minus 4. Centimeters to meters 10 to the power minus 4, right? A small simplification, I have to simplify. Then this is 32 times 10 to the power 4. 10 to the power 4 is 100 times 100, no? Right? Then here 4 times 320 squared, 25 times 25. By 25 is cancels, right? What is simplification at anything that you have to do? Then 25 times 4. Then 4 to 4 cancels. 25 times 4 again, right? Then 32 and make cancel and on. You got one, right? Then this is 32 remains here times 4 remains now. And this is 320 times 320 kilo. We can write it as 32 times 32 times 10, no? Sorry, 100, no? 320 times 320. I separated 10 to the powers. Then 32 to 32 cancels. 4 times 8 is here. 4 times 8. Then M equals 1 over 8. 10 to the power minus 2. 1 over 8 is 1.25. Right? 0.125. Then 0.125 means adjust the value 1.25. 10 to the power minus 3. 1.25. 10 to the power minus 3. That is in the standard unit now, kgm minus 1. Right? That's a small simplification. Yeah, that's it. Any questions? Any questions from today's things? Or is it clear enough? Right? We discussed again 3 questions today. And in my question analysis also, I discuss about this. Listen, right? Something I wanted to highlight. Right? Listen. In last 2 years, right? This question was from optics. In last 2 years, 25 and 24. Right? Both 25 and 24 was from optics. Right? They were from optics. Right? Then we can't say whether optics is coming again or not. Right? But last 2 years was optics. Then probably means a higher possibility. Higher possibility should be with waves, no? Right? Then you better put some more attention on waves. I will discuss few more questions on waves also. Now today, from these 3 questions I discussed, 2 optics and 1 was waves, right? And I will take another day for waves. Last 2 years are from optics. Right, any questions? So is it clear enough? Say clear if that is clear. How was it? Is it clear enough? No questions. No questions, right? Okay, no questions means it's clear, right? Right, okay. Then if no questions, we can wind up, right? We can wind up. Right, so again, it's okay. Okay, thanks. Thanks. So again, what I need to say is, again, we are just 6 weeks, right? 6 weeks, utilize your time, right? Now from my side, I'll be putting question discussions in the future also, right? And sometimes I might increase the days, right? Sometimes in the sense, most probably I will increase the days that we use for the discussions, right? Sometimes in the coming weeks, you will have 2 S2A discussions per week, right? Or another discussion under a different name or different program, right? Komari paper discussions, very right? Now, since the syllabus is also almost over, right? After finishing it, right? The next month, entirely the next month, going to be used for question discussions also in the theory class times, right? Other than that, paper writing, discussions, and everything goes on. Homework, paper writing, and physical paper writing, everything goes on, right? So other than all the things, right? During the time we are getting free means now after finishing the theory classes, those time slots will be free, no? So we'll be utilizing those slots also to question discussions, right? Probably they will be lesson based question discussions, and in there my main priority would be essays, right? But we'll be discussing all types of questions, but giving some more priority to essays. Let's see, we'll do in a balanced manner. All right, then if no questions, we can wind up, right? So thanks for joining, right? Even after the rescheduled time, right? Because I had to reschedule because of some unavoidable consequences, right? So I had to reschedule and shift this to 1 hour, 1 hour later. So thanks for joining, right? Then study hard, work hard, and stay safe, right? See you in the next class. Good night and goodbye. See you.